Today I explain photochemistry lecture number 3, some energy, concept of energy and there's and selection rule for transition and the modified Jablonski diagram and Jablonski diagram. Okay. Now we consider, in the previous lecture I described about the Born-Oppenheimer approximation. That should be the total energy of a system or a molecule or a particle that should be equal to E transition energy plus E vibration energy plus E rotational energy and last one E electronic energy. As for transition energy is not quintage, so we can say that is overall energy equal to E rotation energy, E vibration energy and electron energy. On that case, I only explained about the rotation energy. That is rotational energy. That should be arises when the molecule that should be rotate about an axis that should be perpendicular, means produce 90 degree to the internuclear axis and passing through the center of gravity of the molecule. Suppose a molecule where the center of gravity is present and there should be internuclear axis, so we have to consider the rotational energy can be arises in this center, in this axis, because this is perpendicular to internuclear axis. If internuclear axis is this, so this line will be the perpendicular of the internuclear axis. Okay. If center of gravity present in this position, so obviously the rotational axis that should be passes through the center of gravity. Okay. So on that case, some energy that should be generated, and this is termed as rotational energy. Okay. Okay. So rotation energy arises when the molecule that should be rotate about an axis perpendicular to the internuclear axis and passing through the center of gravity of the molecule. Okay. Means rotation energy arises when the molecule that should rotate in a rotational axis and this axis that should be perpendicular or produce 90 degree to the internuclear axis and obviously passes through the center of gravity of the molecule. Now the question arises, what is term center of gravity? Center of gravity means for each molecule or for each particle or for each electron, there should be any center should be present where whole of the molecules gravity present there. Okay. Means suppose in any particle there should be one point should be there where the whole particle's mass inside of it. Okay. That is termed as center of gravity. As for example, in Earth, we live in Earth, there should be strong gravitational force, gravitational force. So this gravitational force can be maximum in some point, okay, which is too close to the center of gravity of the Earth. Okay. Similar can be seen for each particle, each molecule, each atom and any subatomic particle also. Okay. So as we know, for macroscopic particle and microscopic particle, as their size difference is there, as their speed difference is there, and there are many properties, wave-like properties, particle-like properties, or variation can be seen. So we can consider many terms in macroscopic level and many terms in microscopic level. Okay, there may be different analogy and terminology can be used. But if you consider all of things in generalized, and suppose it all will be same, so you may interrelated everything. Okay. Now the second one, vibrational energy. Vibrational energy that should be associated with the to and fro motion of the nuclei of the molecule, such that the center of gravity that should be not change. Okay. So there should be vibration energy can be generated due to vibration in the motion of to and fro motion. Okay. In the motion of to and fro motion, and during the vibrational motion, the center of gravity that should be not change, that should be unchanged. Okay. Now the last one, electronic energy that should be associated with the transition of an electron from the ground state energy to the excited state energy level of the molecule. Due to why? Due to absorption of photon of suitable frequency. Due to absorption of photon of suitable frequency, that's why electron that should be jump from ground state to excited state, as electron gains some amount of energy. Okay, that's why. So we have to always consider this is also there is not written, always remember of it, that is all electronic energy that should be consist of vibration energy. Okay, all vibrational energy are consist of rotational energy. Okay. All electron energy that should be consist of vibration energy, on vibrational energy that should be consist of rotational energy. Okay. Now always remember, when we always say about energy, but actually energy is what? Energy is what? Can you give the answer? You can use many terms, as we know, that is in terms of momentum, in terms of velocity, half mv square, in terms of momentum, I think p square by 2m. Okay, p is the momentum, linear momentum. You can also write it, that is kbt. Okay, here is the Boltzmann constant. You can say in terms of charge, QE. Okay, so many dimensions, so many rules are there. If you want to define energy, if that should be applicable for electricity, so we justify the definition of energy in one way. Okay, if we taking the concept of mechanical energy, there should be we justify the definition of energy from another way. Okay, so there we have to consider many definition in different way. When that is electric field, magnetic field, many field can be considered. Okay, so when we consider quantum chemistry is very much relatable with photochemistry, because in quantum chemistry there must be many phenomena can be described about the photon, that should be h nu. Okay, and photochemistry that should be concerned about photon h nu. Okay, by this way, that is we Planck, the scientist Planck described the equation that should be more that should be popular one. Okay, that is del equal to h nu. H is the Planck's constant, nu is the frequency of light that should be incident. That should be incident in particular molecule, ion, system, so on. And del E is the difference of energy between two quantized state. Quantized means there the difference of energy level that should be fixed. Okay, that means this is called quantized. And always remember, del means always there should be difference. When there del is given, del means difference. There should be maybe sometimes small d can also be given. This is also termed as this is also terms of difference or change. Okay. Now the molecule absorb energy when it is excited from lower energy state, that is E1, to high energy state. Okay, and emit radiation of the same frequency when the molecules revert from high energy state to the lower energy state. Okay, that should be very much important concept. When molecule jump from lower to a higher excited state, can you answer it? Can you answer it? That because molecule or electron or atom, that should be absorb some amount of radiation. Okay, due to this they get excited, so they have enough energy, so they jump from ground state or lower excited state to the higher excited state. Okay, but when they reach to the higher excited state, they again re-emit this amount of energy and again back to the ground state or first excited state. Okay, so for emission, that is daily the energy defines, that should be E2 minus E1, and for absorption daily equal to E1 minus E2. As for absorption, E1 is greater than E2, that's why E1 minus E2 means E1, that is the energy absorbed from lower excited state minus energy in higher excited state. Okay, and that is emission, that is must be E2, means energy belongs to E2, that is higher excited state minus lower energy state, that is E1. Okay, sometimes energy lost due to going to a higher excited state, there may be daily that should be lower than the first absorption energy defines. Okay. Okay. So thus, when a molecule absorbs energy, there may be three types of changes in the molecule. That should be, there may be a change in rotational level. As we know, molecule having rotational energy, vibration energy, electron energy. So there may be rotational change can be there. Suppose their rotation is 2 minutes per second. Okay, suppose their rotation, that should be 200 times in 1 second. After absorption, they show 400 rotation in 1 second. So rotation overall increases. So that can also be possible. Okay. Okay. Suppose you driving a car and you have a speed. When you increase your speed, obviously your car go fast. Okay. By this way can be rotation also increases or sometimes decreases also. So there may also be a change in vibrational level, which that should be rotational change may be a superimposed. As we know, vibration energy that also be exhibit for many molecules. So there should be can be chance for vibrational changes. Okay, but when vibrational changes that should be occur, there should be some rotational changes also can be seen. As we know, vibration energy consists of so many rotational energy level. So when vibrational change can be seen, there should be obviously some rotational changes also there. As rotational changes that should be consist of vibration vibration energy level consists of so many rotation energy level. So obviously when vibration energy level changes, on that case rotation energy changes also there, and this should be superimposed. Okay. As for example, in any country there should be changes in all over the country, can be changes the all over people who are present in the country, right? Similar things can be there. If in World Cup India having the good performance, not only the whole only the some people will be happy, all over India will be happy, right? Similar things can be there. Okay, now we consider an electronic state may change simultaneously with changes in both vibration and rotation energies. As we know, that is electronic state that should be consist of vibration and rotation changes. So that's why when electronic change can be there, so on that case obviously vibrational and rotation changes can also be occur. Okay. Okay. Now always remember, there should be energy diagram we can consist. That is the energy profile. This is V equal to 0 vibration energy level. That is V dash equal to 0, V double dash equal to 1, V double dash 2, V so. Now consider all V are consist of J value. Suppose there should be so many J value. Okay. V dash consists of so many J value. Similarly, V double dash, that should be consist of so many J value. Okay, but this all over consisted via electronic energy. Okay. Okay, this is called ground electronic excited state. Sorry, ground electronic state. So there should be, you can see, ground electronic state, that should be consist of vibration energy level. Vibration energy level consists of so many rotational energy level. Right? There should be electronic state consists of vibration energy level, and vibration energy level, that is V double dash 1, consists of so many rotational energy. Okay. So we can justify about it, that is when changes about rotational level, there should be only rotational changes. But when vibration changes can be there, there should be so many rotational changes superimposed. When electronic state changes, there should be both of vibrational and rotational changes can be occur. Okay, you can justify this by this diagram. Okay. Okay. Now we can erase all of things. Okay, for your clear study. Okay. If we put so many symbols or so many drawing here, you have to problem, you can face problems to study. Okay, so we should erase all of things. Okay, now the next one, arrangement in increasing order of various energy levels. As I tell about it, that is all electron energy consists of vibrational and rotational energy. Okay, all vibration energy consists of rotational energy. Okay, so by this case we can justify it, that is E electron energy, that should be maximum. Okay, then E vibration, then E rotation, and E transition, that is also minimum. Okay, sometimes many book, in many book given, that is E rotational also consists of many E transition energy levels. Okay, but there should be variation can be seen in books to books. Okay, now associated with each electronic state are a series of vibration energy levels. I say in previous slide. Okay, designated by the vibrational quantum number, that should be V, not nu, that should be V. In class 12, college level, master's degree, you all, even I also confuse about V, small v, and small, that is nu. Okay, which is nu, which is V. So this term is V. Okay, this is not nu. Okay, vibrational quantum number. And associated with each vibration energy level are a series of rotational energy levels, and that should be designated by rotational quantum number, that should be simple J. Okay. Okay. Now again I erase it, all of things. Okay. So now we consider for electronic transition. Okay, there should be so many energy levels are there for each particles, most of the cases molecules. That should be when UV visible applied, okay, especially for UV visible apply, and that should be electronic spectra. Okay, this is sigma, this is bonding, this is pi, this is also bonding, this is non-bonding, this is anti-bonding, this is a anti-bonding. Okay, okay, this is bonding, sigma, pi is a bonding, that is N means non-bonding, pi star means anti-bonding, and sigma is anti-bonding. If sigma is a bonding, its corresponding sigma star should be anti-bonding. If pi is bonding, its corresponding pi star, that should be anti-bonding. And always remember, sigma and pi always exhibit as a bonding phenomena, okay, always they should be bonding. So their corresponding opposites, sigma star and pi star, belong to anti-bonding, okay. And there should be, in between of bonding and anti-bonding, N means non-bonding region will be there, okay. So there must be lots of transition can be there. If we consider alkane, as for example methane, there should be only possibility sigma to sigma star possible, because there is no double bond. If double bond is not present at all, there should be no pi bond. You know that is single bond means sigma bond. And when that is p orbital perpendicular and they made sideways overlap and produce double bond, triple bond, these bonds are considered as pi bond, okay. And pi to pi star transition can only possible for double bond or triple bonds, for generalized multiple bonds, okay. But when single bonds are there, there should be no chance for pi to pi star transition, okay. Again, we come in CH4, there should be no lone pairs are present. For each carbon and hydrogen, both having no lone pair, so there should be no non-bonding electrons. So there should be non-bonding to pi star, non-bonding to sigma star are not possible. So there should be only one kind of transition possible, that should be sigma to sigma star, okay. Similar, when we come CH2 double bond CH2, that should be called ethylene. Here pi bond is present, this to pi bond, so there should be pi to pi star can be possible, and also sigma to sigma star also possible, okay. Pi to pi star and sigma to sigma star both can be possible, okay. Now we consider, suppose CH3 COO CH3 means what? Acetone. There should oxygen having lone pair. Okay, oxygen having lone pair. So there should be non-bonding electrons are present. So there should be sigma to sigma star possible, N to sigma star possible, pi to pi star possible, N to pi star possible. And in this case, we can derive this equation, okay. And for methane or ethylene, we have to consider, if for methane there should be one possibility, this only for methane, okay, only this possibility, okay. If we consider ethylene, there should be two possibilities, sigma to sigma star, pi to pi star. So this can be cut, this can be cut. So this sequence can be observed, okay. And last one, that is acetone. All can be mentioned. High energy is sigma to sigma star, then N to sigma star, then pi to pi star, then N to pi star. In photochemical transition, most probable that is pi to pi star, N to pi star. As sigma to sigma star is high energetic, that is energy order. This is the energy order, okay. So sigma to sigma star is high energetic, that is more energy have to be needed. So this is goes to UV region, we do not see in our eyes. Okay, so n to pi star and pi to pi star, that should be possible. N to sigma star, that is also are not used. Okay, so there must be there should be so many transitions can be possible. Sigma to sigma star, sigma to pi star, pi to pi star, pi to sigma star, and n to sigma star, n to pi star. Okay, now consider there should be sigma to sigma star can be possible. Sigma to pi star is not possible because sigma is, I think, Gerard, pi star is Angerard, Gerard to Angerard, transition not possible. This type of terminology can be there. Okay, this. Okay, Gerard to Gerard, Angerard to Angerard, transition can be possible. So by this way, this is symmetry forbidden. Okay, sigma to sigma, pi star, sigma, I think Gerard, and pi star, that should be pi is Angerard, Angerard to, suppose, Angerard. Okay, sorry, pi is Angerard, sigma is Gerard, pi is Angerard, pi star is Gerard, and sigma star is Angerard. Okay, so there should be Gerard to Gerard transition not possible. That's why this is not possible. Now consider pi to pi star can be possible. That should be Angerard to Gerard. Okay, pi star to sigma star, that also not possible. This is Angerard to Angerard is not possible, forbidden. Okay, and n to sigma star, into pi star, both are possible, both can be possible, but that should be intensity is lower as it is not included in symmetry criteria. Okay, so it is observed that pi to pi star, n to pi star transition occur in UV region, that is 200 to 400 nanometer. Pi to pi star and n to pi star, that is goes to UV region 200 to 400 nanometer. When conjugation increases, absorption due to pi star transition shift to longer wavelength, means visible wavelength. Okay, when only pi to pi star, n to pi star exhibit, that should be the region is 200 to 400 nanometer, that should be goes to UV region, so we cannot see any color of the molecule. Okay, due to transition. But when conjugation is there, there should be the pi to pi star transition shifts to the longer wavelength. Longer wavelength means energy shorter, so that goes to visible range, and due to this we see color. As we can say example, that is ethylene. Ethylene is a colorless. Okay, as it is, there should be one double bond, one pi to pi star transition possible, no conjugation attached with it, so that should be goes to UV region. That's why ethylene is a colorless molecule. Okay, but when we consider beta carotene, there should be beta carotene, there must be lots of double bond CH2 unit is there. Okay, or CH double bond CH unit is there. There should be lots of double bond. So due to this, the color exhibited orange color. Okay, actually there should be so many substituted or unsubstituted CH2 double bond CH2 bonds are there. But as there must be extended conjugation present in beta carotene structure, due to this beta carotene is a orange color molecule. Okay, but ethylene is a colorless, as there is no conjugation, there are only one pi to pi star transition possible, so that should be go to 100 to 400 nanometer. UV region. So we cannot see any color of ethylene molecule. Okay. Now again, if we know Jablonski diagram, this is a Jablonski diagram. Jablonski diagram. That should be the energy diagram. S0 is the singlet state, where the molecule having this type of electron. Okay, spin pair electron. Okay, that should be go S1. So means this and this, and T1 means this and this. Okay, that is S0. S0 means spin paired. S1 means they are not spin paired, but spin that should be unchanged. And T1 spin that should be changed. That should be unpaired and spin change. Okay. First one S0, that is ground singlet state, absorb some amount of energy and go S1. Okay. And other molecule that should be absorb more amount of energy, so they go S2. Okay. There must be possible for a return back, that is S2 to inter-system crossing T2. That is second excited state, second triplet excited state, and that is S1 to inter-system crossing. There should be inter-system T1. That should be first triplet excited state. There must be taking example as this is pi to pi star and this is n to pi star. Okay. Okay. Always remember for S2 to S3 there should be in IC, inter-system crossing, and there S2 to S1 or there should be need IC, internal conversion. Okay. And always remember these are radiative, I think non-radiative transition. Okay. Radiative transitions are basically there should be phosphorescence are there. There should be fluorescence is there. When singlet excited state emit energy and go back to first ground state, that is termed as fluorescence, and that is T1 that should be release energy and go back to S0, that should be there should be phosphorescence. Okay. The difference between fluorescence and phosphorescence nothing but this is the after switching off the light, fluorescence is still there, phosphorescence is not there. Okay, we can discuss about it. If there is any confusion, we will be sort out in next lecture. Okay. Okay. Now the selection rule. First one, molar extension coefficient. That should be designated as epsilon max. That should be probability of transition. Selection rule that should be there. If epsilon max is greater than 0, that means transition allowed. Okay. And when epsilon max is less than 0, transition is forbidden. Okay. On that case, when transition forbidden, intensity that should be lowered. Okay. Now, two types of forbidden transition. First one, spin forbidden transition. Selection rule predict that all singlet to triplet transition are forbidden. If S to T goes, so that should be forbidden. Okay, selection rule predict that all singlet to triplet transitions are forbidden. So similarly, phosphorescence is a forbidden process and fluorescence is a allowed process. Okay. Explanation: an electronic transition in which spin multiplicity of the electron remains the same in both ground and excited state, that must be del S equal to 0, means the transition is allowed. So spin selection rule that should be defined as, that is del S, that is overall change in spin, that should be 0. Actually no spin change can be occur during the transition, then the transition will be called as allowed transition. So for allowed transition, spin that should be unchanged, that means del S equal to 0. But when But when that is singlet to triplet transition can be possible, so on that case del S not equal to 0. Spin that should be changed. Okay. That's why this transition, that is singlet to triplet transition, that should be forbidden. Now, change in spin multiplicity involves a change in angular momentum. Obviously, when spin multiplicity change, so angular momentum also change. And such a change violates the law of conservation of angular momentum. Okay, when spin multiplicity change, on that case angular momentum change, and that's why these changes violates the law of conservation of angular momentum. So therefore, singlet to singlet and triplet to triplet transitions are allowed, but singlet to triplet as well as triplet to singlet transitions are forbidden transition. So that's why, as we know, for singlet to triplet, del S is not equal to 0 and spin that should be changed. As spin change, so angular momentum change, so that should be violate law of conservation of angular momentum. That's why singlet to triplet and triplet to singlet are forbidden process. But correspondingly same analogy as spin are not changing in transition of singlet to singlet and triplet to triplet transition. So singlet to singlet and triplet to triplet transitions are allowed transition. Okay. So however, this rule is not obeyed in certain cases, most of when heavy atoms such as iodine present in a molecule. When iodine is present in a molecule, on that case this rule is not obeyed. So in such cases singlet to triplet transitions are take place. Okay. So when S1 to T1 is goes, there should be energy needed, and this is called there should be this process is termed as inter-system crossing, and that should be the forbidden process, as this is violate the spin selection rule. Okay. Now we consider symmetry forbidden transition. These rules state that ungerad to gerad and gerad to ungerad transitions are basically allowed. Ungerad to gerad and gerad to ungerad. But gerad to gerad and ungerad to ungerad transitions are basically forbidden. Okay. Explanation. An electronic transition proceeds more rapidly when the wave function of the initial and final state closely resemble to each other. When initial and final state that should be resemble to each other, on that case electron transition proceed more faster way. That's it. That is, the transition is allowed on that case. Okay. When the initial and final state are exactly resemble, that means they are resemble to each other. Okay. Match for each other. So on that case electron transition will be faster way and the transition will be allowed. Okay. So pi to pi star transition is allowed transition, as pi and pi star orbitals occupy the same regions of the space, and so they overlap to much larger extent. So pi and pi star match for each other. Okay, this is the best example, match for each other. So their overlap should be the more larger extent, so they are allowed process. Therefore this transition is allowed. But n to pi star overlap is our small extent overlap. As small extent overlap, that's why we consider that this transition is forbidden. Okay. But this n to pi star transition is weakly allowed due to coupling interaction. But n to pi star transition can be seen in many molecules. If this transition is forbidden, so how we can conclude they can be seen? As there should be some coupling interaction between vibration and electronic motion of the molecule. Due to coupling, n to pi star transition can be weakly allowed. As coupling interaction between vibration and electronic motion in the molecule can be seen, that's why n to pi star transition weakly allowed. Okay, but as weakly allowed, not strongly allowed, so n to pi star transition intensity that should be lower than pi to pi star transition. Okay. Okay. Now our absorption of light photon, the electron of the absorbing molecule, say jump from S0. S0 is the ground excited state. S0 to S1, S0 to S2, S0 to S3. Okay. Singlet state depending upon S1, the energy of the light photon absorbed or shown Jablonski diagram. Okay. For each singlet excited state, that is S1, S2, S3, there should be corresponding triplet excited state. That should be T1, T2, T3. For S3 we get T3. For S2 we get T2. For S1 we get T1. Okay, there should be for each singlet excited state we get same amount of triplet excited state. Okay. Okay. So whether the singlet or triplet excited state is said to be activated, because molecule get activated, then they go to the singlet excited state and triplet excited state. Otherwise, they always belongs to the ground singlet state, where the spins are not changed and the actual spins are paired. But in singlet excited state, spin that should be become unpaired, but spin is unchanged. And triplet excited state, electrons are unpaired, but their spins that should be changed. Okay. So when the molecules do not get activated, do not get any type of energy, they always belongs to the ground singlet state. That is S0. That should be S suffix 0. When they get some amount of energy and get excited, then they can go singlet excited state, that is S1, S2, S3, and their corresponding triplet excited states, that should be T1, T2, T3. Otherwise not. Okay. So that's why we can see if A0 is the molecule, that should be absorb H0, certain amount of energy, they can be activated to produce A star. A star is activated molecule. Okay, A0 is the molecule in the ground state and A star is the molecule in the excited state. Okay. Now again in the picture you can see there should be, when singlet to singlet and triplet to triplet transition is there, that should be termed as IC, internal conversion. That should be called as internal conversion. Okay, that can be seen also. Okay, that can be seen also there also. That is S1 to S0 also internal conversion can be take place, and T1 to S0 there should be inter-system crossing can also be there. Okay. When S3 to T3 can come, that there should be inter-system crossing. S2 to S1 come, inter-system crossing, and S1 to S3 come, there should be inter-system crossing. Now, there should be other type of radiations are there. That is, there should be fluorescence from S1 to S0. There should be phosphorescence from T1 to S0. That is S1 to S0 fluorescence and T1 to S0 phosphorescence, and there should be, this is our absorption. Okay. Now the bigger modified Jablonski diagram. Okay. Modified Jablonski diagram, there should be so many things are there. Suppose first one, that is there should be S0, ground singlet state. Okay. So due to absorption, that should be go S1, that should be go S2. Okay. There should be S1 to that should be go, and this is termed as S1, this is termed as S2. They are absorption. Okay. But now when S1 to S2 to S1 come, that should be termed as internal conversion. That is 10 to the power minus 13 to 10 to the power minus 14 second. When S2 to S1 come, that should be termed as internal conversion, 10 to the power minus 13 to 10 to the power minus 14 second. When S1 to T1 come, that should be called inter-system crossing, ISC. Okay. When S1 to T1 come, that should be termed as inter-system crossing. Okay. That is, this is S2 to S1 and this should be S1 to T1. Okay. These are termed as inter-system crossing. That 10 to the power minus 6 second. 10 to the power minus 6 second. Now, for T1 to T2, there should be absorption. And for T1 to T2, that should be called as IC, inter-system crossing. Okay. Now for T1 to H2, that should be termed as fluorescence. That is T1 to H2, that should be termed as fluorescence. And that is value 10 to the power minus 5 to 10 to the power minus 3 second. When T1 2, that is first triplet excited state to ground singlet state, transition can be there, that should be termed as phosphorescence, 10 to the power minus 5 to 10 to the power minus 3 second. Okay. And when S1 to S0 are come, that should be termed as fluorescence, and that is should be 10 to the power minus 5 to 10 to the power minus 6 second, 9 second. That should be termed as S1, that is first singlet excited state to ground singlet state, fluorescence can be occur, that is lifetime will be 10 to the power minus 5 to 10 to the power minus 9 second. And this is the absorption, that is almost 10 to the power minus 5 second, 10 to the power minus 5 second. Now always remember this a transition with the absorption of emission of radiation. So that is radiative transition. So that is which are radiative transition? Basically absorption, fluorescence, phosphorescence. Phosphorescence, fluorescence and absorption are termed as radiative transition. Now we come non-radiative transitions are basically inter-system crossing and internal conversion. That should be belong to the non-radiative transitions. That's why in that case both type of transition can be there. This is our non-radiative transition, that should be termed as IC. This is the non-radiative transition, that should be termed as ISC. Okay, this is also non-radiative transition, that should be termed as ISC. Okay, and this red colored are the radiative transition, that is absorption. Okay, they are also radiative. This is fluorescence, that is also radiative. And this is phosphorescence, that is also radiative. Okay. Okay, so modified jablonski diagram, lifetime of excited singlet state, that is maybe S1, S2, S3 so on, that should be 10 to the power minus 9 second to 10 to the power minus 5 second. Okay, lifetime of excited singlet state. Okay, 10 to the power minus 9 second to 10 to the power minus 5 second. Lifetime of excited triplet state, that should be 10 to the power minus 5 to 10 to the power minus 3 second. 10 to the power 5 minus 5 to 10 to the power minus 3 second. So from this, what we conclude? That is more time 10 to the power minus 9 is large or 10 to the power minus 5 is large. 10 to the power minus 9 means 1 by 10 to the power 9. And 10 to the power minus 5 means 1 by 10 to the power 5. So which is more large? 10 to the power minus 9, I think. Okay, next there should be confusion. Minus 5 to 10, actually minus 9. I think this should be the short lived. Okay, this is short lived and this should be longer lived. Now lifetime of excited state 10 to the power minus 4 epsilon max. Okay, so there should be concluded, that must be this should be the to the power minus 4 and this is short lived and this is much more time lived. Okay. If in this I will be check and next day I will be say about in the lecture. Okay. Thank you. You can draw this picture or take screenshot, okay, for better representation. Okay. Okay, thank you so much. Now the class today end. After the next lecture will be discussed in other topics of photochemistry also. Okay.